Okay, thank you for your patience. Let's talk some more about the logs and exponentials. Actually, what we've been talking about is just the logs with no reference to exponential functions at all. But today I want to sort of tie it into exponential functions. Of course, everybody knows that the logarithm is somehow related to exponential functions. And as I've said, probably the way that this is presented in your high school class or whatever was you learn about the exponential function first, and then the log is defined to be the inverse of that. But you can define the log just using an integral. That's the way that we have been presenting things. And I will just remind us of the graph of the natural log. I should put it up here. I should put it in the middle too. Sorry. The graph of the natural log looks like this, right? This is ln of x. And there is this, that is 1, right? And there's the special number e that we discussed briefly last time, which goes sort of here, where y equals 1. This value here is e, all right? And that's the definition of e. It is the number, the x value, for which ln of e equals 1, all right? There is some number, and that's the number that we call e. And it has some, it's an irrational number, 2 point something something. It usually doesn't matter what exactly the number e is. All right, anyway, this is the function y equals ln of x. And today I want to talk about the inverse of that. So in order to even talk about the inverse, it is necessary that this function be 1-to-1, but it is. I mean, 1-to-1, remember, means that it passes a horizontal line test. That is, every horizontal line through this curve touches the curve exactly once, and that is true. So that means there is an inverse. So the natural log of x is 1-to-1. So there is an inverse function. And what is the graph of the inverse function look like? Remember, the graph of the inverse function always looks like a mirror image around this line, y equals x, all right? So the graph of the inverse function looks like this, and it goes through 1, because it has to line up with the other one, right? Everything has to be mirror imaged like that. And this function, the inverse of the ln, is what we are going to call, so ln of x is 1-to-1, so there is an inverse function. We call it, at least for now, I'm just going to write it this way, exp, and you'll see why in a moment we use that name for it. The inverse of ln x is, I'm going to, for now at least, write it as exp of x, and this is referred to as the natural exponential function. All right, this is somewhat weird terminology to use here, but it's because I call it the natural exponential function because it's the inverse of the natural logarithm. All right, and of course you probably know there are such thing as other logarithms and there are other exponential functions, but this is the kind of the nicest one, or the one that we're going to most often want to talk about. All right. And one thing that you can see right away on the graph is, so this is directly from the graph, it's that exp of 0, that is, if you plug in x equals 0 to that function, the new one that I drew up top here, this one, if you plug in x equals 0, you get 1. So exp of 0 is 1. And also, because of this value, it means that if I, well, it means something else. Maybe it's, e is the one where ln of e equals 1. Because this is the inverse, it means exp of 1 equals e. It's the other way around. Exp of 1 equals e, right? It's because this function is the inverse of ln, and ln has ln of e equals 1, so this has to be the other way around. Exp of 1 equals e, all right? All right. Great. Some properties of this exp function, and I'm going to stop saying it sounds silly to say exp like that over and over again. We don't usually call it that for reasons that you will see in just a moment. We don't usually call it exp. Instead, sorry, I lost my train of thought because of the screen. I just noticed that it's like zoomed in a slightly weird way, and that's distracting me. I'm not sure why. I'll try not to think about it. What was I saying? All right. Let's talk about, so remember, sorry. I forgot that we were in this classroom this morning also. I started to walk to the other one. I'm all disoriented. Remember this rule about the natural log? ln of x to the n is n ln of x, right? And also, of course, ln of e equals 1. That's the point of this number, e. If we sort of put those two rules together, so do both of these, this means ln of e to the n. What is that? Well, we can use the first of those two rules about the n and bring the n to the front. So it's that. But then I just said ln of e equals 1, so this is just n times 1, right? So ln of e to the n equals n, right? And this is true for any n, any real number n. And what that means is, so the inverse of ln of x is e to the x. Because this means when you plug one inside of the other, they kind of cancel each other out. And that's what it means to be the inverse, right? Here I wrote it with an n, but this might as well have been written with an x. And it says the ln and the e kind of cancel each other out, and you get back to what you started. And what that means is, so this, what I was calling exp of x, is actually the same function. It's actually the same as e to the x, all right? And that's why e to the x sometimes is referred to as the natural exponential function, although usually people just call it e to the x, all right? It is the inverse of the natural log function. It is the same as e to the power x, where e is that number, and this means the exponent, e to the power x, all right? So that means I'm not going to write or say this exp anymore. This thing right here, actually this function is the same as the number e to some power of x, all right? And this is where the connection between logs and exponential functions comes from, all right? The natural log is defined to be the area under the curve of 1 over t, and the inverse of that turns out to equal the exponential function e to the power x, all right? I think this is probably something that all of you knew already. What's sort of different about our approach in this class is just to define it in the other way around. We define the natural log first and then derive properties about the exponential function based on that. All right? Okay, great. One thing that's important about this is this means we can use sort of ln and also e to the x, ln x and e to the x, to solve equations where x appears inside an exponent or inside of a log. And this is important from time to time, to solve equations where x appears inside an exponent or inside of a natural log. For example, and this is all based on using these as inverses of one another. So if you have something that says like ln of a equals b, this means that e to the b equals a. It's because they are inverses of one another. So when you see an equation involving ln, you can change that into basically the same equation involving e's, but it's the other way around. So here I have a inside the log, here I have b inside the exponent, all right? That's what it means that the log and the e are inverses of one another. It means whenever you see an equation written in terms of logs, you can always rewrite that equation in some kind of exponential form. And the other way around also. If you have an equation written in terms of exponents, you can rewrite it in terms of logs. So this is referred to like these two statements are really saying the same thing. It's just writing it one way or another way. So this is sometimes called a logarithmic form of writing this thing. The logarithmic form, and this is the exponential form. And by interchanging one for the other, it can help you to solve certain equations which actually you have no way of solving in other ways. Like this is the typically the only way to solve an equation where, for instance, x appears inside an exponent. All right, so let's check it out. How about if I wanted to, say, solve for x inside an exponent? For example, this might look something like 4e to the x minus 2 equals 7, and your job is solve for x. Maybe you've done this before. The way to do it is, this formula is written in an exponential form, and x is inside of the exponent. We can get x out of the exponent by rewriting it in a logarithmic form. So the first thing that we should do is, like, I want to write it like this so that I can change it into that. I want to write it as this exponential format so that I can change it into this logarithmic format. It's not quite there because of this 4. So the first thing that you should do is just like isolate the e to the whatever, right? So I'm going to do that by dividing by 4. E to the x minus 2 equals 7 divided by 4, all right? You have to put the e all by itself on one side before doing the next step, and that is, this is now in the exponential format. I am going to write it in the logarithmic format. And so you have to be a little bit careful here, but what I'm doing is, look at these two sort of red boxes here. What I have right now looks like this. E to something equals something. I'm going to translate it so that it looks like this. So it's going to say ln, ln of something equals something, and it has to be just kind of like the opposite. So instead of 7/4 being on the right, I put the 7/4 inside of the natural log. And then instead of x minus 2 inside the exponent, it goes over here. All right? You just kind of switch everything around. What used to be on the inside becomes the outside, and what used to be on the outside becomes the inside. All right? But anyway, now we can indeed solve for x. And in fact, this is basically the only way to solve for x in an equation like this. When x is inside of the exponent, you have to do something like this to get it out of the exponent. And anyway, now we can solve for x. X equals, you add 2, right? So it's 2 plus natural log 7/4. There you go. This is how we solve for x inside of an exponent. You must use the natural log. There really is not another way to solve for x in a situation like this. All right? And this is really the principal use of logarithms in real life. Like, logarithms are useful in the real world, and this is typically how they are used to solve for something which is inside of an exponent. All right? And in real life, this happens all the time, or this comes up all the time, because exponential functions are very common in nature, and you do often want to solve. All right, let's talk about, you can also do a similar trick, but the other way around, to solve for x when the x appears inside of a log. So to solve for x which appears inside of a ln, something like this. 12 equals 2 ln of 10x plus 1. Solve for x. All right. Again, I'm going to do the same trick where I interchange one exponential format for a logarithmic format, but this time it's the other way around because I start with the log. Anyway, the first thing you have to do is sort of isolate the logarithm, and to do that I'm going to divide by 2 first. just to get it started. So divide both sides by 2. It says 6 equals natural log 10x plus 1. All right, that's just to isolate the log part. And then I'm going to interchange this logarithmic format for an exponential format. So again, I'm looking at sort of those two red things up the top there. What I have all the way at the bottom is written as a log. I want to change it into an exponent. So what was inside the log moves to the outside all by itself, and what was on the outside, the 6, becomes the exponent. So when I write this in the exponential format, it says e to the 6 equals 10x plus 1, like that. This can be slightly confusing when you're trying to work this out, but that's how it goes. What was on the inside of the log just ends up by itself, and what was on the outside, the 6, ends up inside the exponent. All right, and now we can solve for x. So I would subtract the 1 to the other side. 10x equals e to the 6 minus 1, and then divide by 10. I'll write it like this: 1/10 e to the 6 minus 1. And of course, if you really want, you could plug that into your calculator. That's what x is. All right. Any thoughts about that one? Any questions? I got some of these for you to try just to make sure everybody is with it. I hope that you've had some kind of experience with this. How about solve for x in here? E to the 2x plus 1 equals 5. And let's try 4 natural log 3 plus x plus 2 equals 8. How about that? See if you can solve for x in each one. They are similar to the ones that I just did. That says plus 1 up there. Yeah, sorry, that's not clear. Plus 1. I'll write down what I got slowly here. let's talk about these. Looks like people did great. The first one, everybody seems to have settled on this. Some people wrote it as a big fraction with a 2 in the denominator, and that's totally fine. Any questions about that one? I think everybody worked it out. This one over here, I would start, you have this, I want to isolate the log, right? And I have this 4, and I also have this plus 2. In order to isolate the log, the 4 here is multiplied only onto this. It's not 4 times the entire left-hand side. So I have to, in order to isolate this log, I have to subtract the 2 first. It should say 4 ln 3 plus x equals 6. And then divide the 4. ln 3 plus x equals 6 over 4. And now this is sort of in the standard logarithmic form, and I can translate this into an exponential form. It will be the other way around. E to the 6 over 4 equals 3 plus x. And then subtract the 3, and that'll do it. Minus 3, like so. That's what I said. I hope you got something like that. A lot of people simplified 6/4 to 3/2, which is great. You do you. All right, excellent, great. I hope that those all sound good to you. Let's talk about properties of this e to the x function. Now, I think everybody already knows like properties of exponents and such, but I thought it might be interesting, and we're not going to go crazy about this, but here's properties of e to the x, all right? They are the standard properties of exponents. So, including e to the power x plus y is, anybody recall, what can you do with that? If you have addition inside of the exponent, you can write this instead in a different way. Yeah?
Is it e to the x times e to the y?
E to the x times e to the y. Yeah, you got to kind of keep it straight. If you have addition upstairs in the exponent, that is the same as multiplication downstairs, like that. And then there's also this rule about, there's a similar one with subtraction. This is e to the x divided by e to the y. And there's a similar one with power inside of a power. I'll write it that way. E to the x to some other power. What do you do? Anybody remember what do you do in this situation? This is like, x cubed squared or something. You multiply the powers. Yeah, this is the standard way to do it. And these are basic, actually, like as written, they're not really special properties of e to the x. This is true of any kind of exponents. This is just how exponents work in general. But I want to demonstrate that actually you can prove these. I mean, if you didn't already know these properties about exponential functions, we can prove these using logarithmic forms. Right? For example, this first one here, and we're not going to go through all of these little proofs, but this first one here, you can look at this. So to show e to the x plus y equals e to the x e to the y, well, this is the same as, and this is a little weird, so this is in exponential format, e to something equals some other stuff. I'm going to write it instead in the logarithmic format, which will say log of this equals x plus y. ln of e to the x e to the y equals x plus y, right? This is the same old trick. It's a little weird looking because of all the e's in there, but this is the same process of rewriting the exponential format in a logarithmic format. And now, can we demonstrate why this is true? So this is true by the properties of the natural log. Check it out. If I do ln e to the x e to the y, that is, what can you do with that using properties of the log? Anybody see where I'm going with this? Yeah? Yeah, right. This is the property of the log about log of AB is log of A plus log of B. We've talked about that several times. And then what is ln of e to the x? Well, those are inverses, and so that answer is just x. And what is ln of e to the y? Those are inverses, and so the answer is just y. And that's what we wanted to show. All right. So this is, remember that's what I said. I was trying to demonstrate ln e to the x e to the y is the same as x plus y, and it really is by the properties of the ln. So the moral of the story here is, like these things that I wrote at the top here, properties of e to the x, they are of course just ordinary properties of the exponents, but even if you didn't know that, you could still demonstrate these by using the logarithmic properties. All right. So it's like everything you ever learned about exponents. If they wanted to, your teachers could have taught you about logs first and then taught you about exponents later. They didn't, because that would be crazy to try and teach kids about logs before teaching them about exponents. But it really is. They are just like two kind of symmetrical, sort of opposite sides of the same coin. Anything you can say about exponents, you can also say similar things, but kind of backwards about logs, and the other way around also. All right. I don't think we need to go through the others, but I just demonstrated the proof of that one. These two are also, you can prove them using logs in similar ways. All right. Great. We got some time remaining. Let's talk about a little sort of calculus using e to the x. So let's talk about derivatives with e to the x. Derivatives and antiderivatives. Maybe you already know the punchline here. Derivatives with e to the x are actually very easy to handle. There is a formula for the derivative of e to the x. Now, if you don't already know this formula, how would you figure that out? Well, if I start with, let's just start with e to the x written as a function like that, and let's try to find the derivative. Now, if you don't already know the derivative of e to the x, then you're kind of immediately stuck here. You can't just like find the derivative out of nowhere. But we do know the derivative of ln x, all right? And so to find the derivative, I'm going to use the logarithmic form, because at this point, at least, we actually know more about the logarithms than the e to the x. So to find the derivative, use the logarithmic form. This I will translate into the logarithmic form, which will say ln y equals x, right? This business of translating from the exponential to the logarithmic can be confusing. You got to make sure you keep everything straight, but I hope that it's looking okay to everybody. And now this, we can take the derivative on both sides. Actually, what we're doing here is called the implicit derivative. Take the derivative on both sides. I'm not going to make a huge deal about doing the implicit derivative is a thing that I hope you learned about in Calc 1. Anyway, on the left side, ln of y, the derivative of ln of something is 1 over whatever. So this becomes 1 over y. And then because of the chain rule, I have to multiply times y prime. That's the implicit derivative on the left side. On the right side, the derivative of x is just 1, as it always is. And we can solve for y prime. So y prime equals, if you just multiply both sides by y to solve for y prime, it'll say y prime equals y. That's the derivative, although it's a little unsatisfying to have a y on the right side as part of the answer, but you can still see it at the very top. Y equals e to the x, so I can just plug that in here. So y prime equals e to the x. All right? And now you see why I said actually doing derivatives with e to the x is very easy. It's because if you start with your function as e to the x, the derivative is also e to the x. So this is, just to summarize and put it in a box, derivative of e to the x equals e to the x. And this is really what, when your friends ask you, like, what's so great about e to the x? Why do you got that e to the x neck tattoo. What's so great about that? You say this. I mean, this is really the important property of e to the x. From the point of view of calculus, this is why people care about e to the x, and this is why it is an interesting function to use in calculus. I shouldn't really say why people care. I mean, another reason to care about e to the x is because actually it appears in nature a lot. But in terms of like from abstract mathematical point of view, this is the important property of e to the x as a function. All right? It means that doing derivatives with e to the x tends to be very easy because you get the same function again. Now, that formula by itself is not terribly interesting. More often, I will say usually, we have, sort of other stuff in there. That's supposed to say stuff. Other stuff in there. For example, what if I want to do the derivative of e to the some other stuff? If there's another function of stuff up there, maybe it says e to the x squared or e to the 5x plus 2 or something like that. How do we handle that? Well, that would be handled using the chain rule. The chain rule says we do the derivative of the outside part, which is the e, followed by or the derivative of the outside part with the same thing on the inside, and then times the derivative of the inside. So when I do derivative of the outside part, which is the e, I just get the e again, because that's what it says in the box, with the same thing on the inside, and then separately you multiply times the derivative of the inside. That's the chain rule. So this, if you like, you could put this in a box and memorize that, although, as I've said before, I don't really have this memorized per se. I just remember that if you have some other weird stuff up there, you have to multiply times the derivative of the inside stuff because of the chain rule. All right. But if you like memorizing stuff, you can memorize this this formula here. All right. This is how you take the derivative of e to some bunch of stuff. All right. So, like for example, what is the derivative of e to the 3x squared plus 7x? What it says in the box there, or doing the chain rule, it says you do the derivative of the e part, which gives you the same thing again. And it really is the same thing. Don't also take the derivative upstairs, right? It is the same thing again. And then, separately, times the derivative of what was on the inside. And that, in this case, it would be 6x plus 7. All right, so that's the using the chain rule to find the derivative of some exponential function. All right? These are typically, fairly straightforward to do. You just got to know how to do them. I got a few for you to try. See what you think about. How about each time take the derivative. E to the sine x, e to the square root x. Here's a crazy one. That's a big fraction inside the exponent. And then there's another one. See what you think. Find the derivative of each one. Okay, good. So leave it right there. Good here. Great. Still good here? Mm-hmm.
Can you just leave like that or
Yes, you should go with that. One of these you probably should use the quotient rule for, but I don't care if you simplify after doing the quotient rule. I'm not into that. Yeah, you know that, like. Great. All right, can we discuss? The first two, I mean, horizontally at least, are fairly straightforward. So here, the derivative of this is e to the sine x times cosine x. And I think pretty much everybody said that. You just keep the same thing again, and then you multiply times the derivative of the inside. Okay, this one, the derivative of this is the same thing again, and then times the derivative of the inside. The inside was root x. You should think of that as x to the 1/2 power, and so the derivative of that shall be 1/2 x to the minus 1/2. That's how I'd write that. I saw some variation on writing that, which is fine. Any questions about those two? I think those were the more straightforward ones. Okay, this one, to do this derivative, you should be, in my opinion, using the quotient rule, although there are other ways that you could rewrite this, but you get the same thing again, e to the 3x over x squared plus 1, and then times, here I'm going to do the quotient rule, so the derivative of that original fraction, and I hope everybody remembers the quotient rule. It's not going to come up all that often this semester, but I mean, every so often it might come up. It is the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. So it's this minus the top times the derivative of the bottom divided by the bottom squared. That's the quotient rule. If you wrote the multiplications in a different order, that's fine, although it does have to be this one first and then this one. If you swapped these two, then it's backwards. The minus sign makes a difference there. So I hope you got something like that. I don't care if you simplify it beyond that point. All right. And then the last one. What was your strategy for this one? This one's a little different from the others. Did anybody feel like it was different? It's okay to be different. Nobody's saying. This one, in my opinion, is different because there's sort of two parts here, right? There's the x and the e to the 5x, and they're being multiplied. And so overall, this is a big product rule. You must do the product rule here. So, and I hope everybody remembers the product rule. It is the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. Or you could write it in the other order. It doesn't matter. So what I just said, the first thing times the derivative of the second thing, that will be e to the 5x times 5. That was the derivative of e to the 5x. Same thing again, times the derivative of the inside. And then plus, that was the first half of the product rule. The second part times the derivative of the first part, that's just e to the 5x times 1. This is the second part. This is the derivative of the first part. That's what I got. Any thoughts about that one? All right, excellent. We have 4 minutes remaining. I think that's enough time for me to just say one more thing. Those were all derivatives of e to the x. How about antiderivatives of e to the x? All right, since the derivative of e to the x equals e to the x, reading this the other way around, it means the antiderivative of e to the x equals e to the x, right? If the derivative of this is this, it means that the antiderivative of this is this. And they're all the same, right? So since that, I don't have to say so. Also, this means integral e to the x dx equals e to the x. Don't forget the cupcake, plus c, all right? So for example, let's just try one. Again, that formula, so put this in a box or something. That formula just straight up by itself, it doesn't come up all that often. Usually it's somehow couched inside of other stuff. So let's try one, and this will do us for today. How about this? This is an integral involving some e stuff, all right? But it's got extra stuff on the inside. Now, when you see extra stuff inside of other stuff, the appropriate trick to use is the u substitution. So I'm going to go u equals the inside part. When I say the inside, usually I mean the inside of parentheses or something. But in this case, this is the inside of the e, right? You don't see parentheses like literally written here, but there is still an inner part and an outer part. So I'm choosing u to be the inside of the e. Now, what's the du? We got to go, so I'm just going to see if we can make this happen. The du is the derivative of the u, which is 3x squared dx. And then, as usual, I'm going to divide the constant there, put the 3 on the other side, because that's usually how this works out. 1/3 du equals x squared dx. And at this point, I look over here and I see x squared and dx, and I start to feel good about this. I think this is going to work because the x squared here inside the integral matches this x squared here. So when I do the plugging of everything in, it says x squared e to the u dx. If I move those around, e to the u, x squared dx, and x squared dx is 1/3 du. So this says e to the u times 1/3 du. And I bring the 1/3 out. This is just a typical u substitution, you know, plugging everything in where it's supposed to go. 1/3 integral e to the u du. And now what is the integral of e to the u? Well, in the box up there it says integral e to the x is just the same exact thing again. So when I see integral e to the u, of course I have the 1/3 already. Integral e to the u is e to the u. So this is just that. All right. This step, it kind of looks like nothing happened here. The integral sign just disappeared. It's not that nothing happened. It's just that it is a fact that the integral of e to the u equals e to the u. And so these are equal. All right. And then just the last thing, as always, I put the original variable back in. So 1/3 e to the, what was it? X cubed minus 1. There you go. That'll do it.